Welcome back to Enzyme Kinetics, Parameters of Enzyme Activity. This time, we will review the equations and graphical solutions for chemical kinetics. To get the most out of the videos, I recommend watching them in order. This is a reminder that this presentation is Dr. Johnson's intellectual property. In a first-order reaction without equilibrium, reactant A is converted into product P with a rate constant of K1. The rate of this reaction is the change of concentration of A with time, or K1 times A. If we add equilibrium into the picture, there is a reverse reaction, conversion of product to reactant with a rate constant of K-1. The equilibrium of this reaction is K1 over K-1, or P over A. The rate is K1 times A, like we saw without equilibrium, or K-1 times P. Usually when we set up kinetic studies, we are careful to operate under initial reaction conditions where equilibrium is virtually non-existent. If we plot the change of substrate concentration as a function of time, we get a curve. It is really difficult to get accurate kinetic data from curves like this without a curve-fitting program. However, if we plot the natural log of A as a function of time, we get a straight line with a slope of minus K1. An alternate approach is to plot the change of product concentration. The graphs of this have the same shapes, but the inverse of the plots using substrate. In a second-order reaction, reactants A and B are converted to product P with rate constant K1. Now the rate of this reaction is K1 times A and B. To get a linear plot, we need to plot the inverse of one of the reactant concentrations as a function of time. This plot has a slope equal to the rate constant and a y-intercept equal to 1 over the initial concentration of the reactant we plotted. In order to simplify second-order reaction kinetics, we can adjust the concentrations of the reactants so that one of them is limiting and the other is in excess, usually by a factor of 100 or more. These conditions allow us to treat the reaction as if it were a first-order reaction. We call this pseudo-first order. The resulting plot looks like the first-order plot with a slope of minus k. Now we have laid the groundwork for understanding enzyme kinetics, which is up next.